Welcome to this explainer. Today, we're doing something a little different. We're going to completely skip the usual heavy math jargon and jump straight into this absolutely revolutionary geometric way of looking at computation. We're diving into a fascinating text that totally reframes one of the biggest, most stubborn unsolved mysteries in all of mathematics, P versus NP. But, we aren't looking at this as a boring problem of computer processing speed. Nope. Instead, we're going to view it as an unbreakable law of geometry. For decades, right, this whole does P equal NP thing has been treated strictly as a barrier of algorithms and time, just machines crunching numbers. But the source material we're exploring today asks us to do something wild. Imagine computation space as something you can actually hold in your hands. It poses this wonderfully physical question. What if the absolute hardest problem in computer science is, quite literally, just a tangled knot? Think about it. When we talk about computation, what are we really doing? We're talking about folding and organizing information. And just like a real physical piece of string, there is a fundamental limit to how small or how tight you can compress that structure. As this quote from the text perfectly captures, P versus NP isn't just about the limits of machines. It is a rigid geometric law. The knot cannot be pulled tighter than tight. How great is that phrasing? Okay, so to understand how abstract math suddenly becomes a physical object, we really need to define our fundamental building blocks, what the source calls Gnosis primitives. And we're going to start right here, with this concept of rope length. In physical terms, it is exactly what it sounds like. It's the absolute minimum length of rope you need to tie a specific knot. A simple loop, well, that requires very little rope, but a complex, heavily tangled trefoil requires a lot more. So try to think of this length as the bare minimum computational resource required to solve a problem. Next, we map this physical rope directly to the code using what's called a Betti's signature. You can kind of think of this as the topological fingerprint of a problem space. The first number in this signature basically counts connected components, essentially the baseline existence of the problem itself. Then, the second number counts the independent branching solution paths, or cycles. The core idea is simple. The more complex the problem, the more cycles it has, and therefore, the larger that Betti signature becomes. And to complete our set of rules, we have the Clinamen cost. This dictates that every single computational step a machine takes costs exactly one lift, which equals +1 topological charge. Practically, this means a machine running in standard polynomial time, what we call the P-space, has a strict, limited Betti budget to spend on its calculations. It's exactly like a financial budget, really. Simply put, you can't spend rope you don't have. Now, this establishes two completely distinct computational battlegrounds. On one side, we have the P-stratum. These are the unknots. They're smooth, they're simple, and their rope length easily fits within a standard polynomial budget. But over on the other side, we have the NP-stratum. These are deeply tangled, messy knots whose required rope length grows exponentially. So the entire core conflict of computer science really boils down to this physical battle between the simple unknot and the tangled knot. So, you're probably wondering exactly how much rope does this NP knot actually require? Well, for an NP solution space handling n Boolean variables, its exponential minimum rope length is exactly 1 + 2 to the power of n. Let's break that down. The 1 is that first Betti number for the connected component we talked about earlier, and the 2 to the power of n represents this massive branching explosion of independent solution cycles. It grows incredibly fast. And here is the absolutely crucial realization of this whole text. No matter how hard you try or how clever your algorithm is, you physically cannot pull this NP knot tight enough to make it fit within a polynomial rope length. The source explicitly defines this as the rope length gap theorem. There is a fundamental, structural, completely undeniable gap between the budget a normal polynomial computer has and the physical amount of rope required to tie that NP knot. Let's actually look at the mathematical proof for this, which provides what are called explicit witnesses. These are exact moments where the NP computation entirely bursts right out of the polynomial budget. For a polynomial of degree 1, it happens almost instantly when n equals 2. For degree 2, the knot outgrows the budget at n equals 5. And for degree 3, that breaking point hits right at n equals 10. Actually, let's zoom in on that separation at degree 3 just to really see the physical impossibility here. With 10 variables, a polynomial budget of degree 3 gives us 10 to the third power. That is exactly 1,000 units of allowed rope length. But if you calculate the npop rope length, 1 + 2 to the 10th power, you get 1,025. The npop knot explicitly requires 25 more units of rope than the absolute maximum budget allows. It just literally doesn't fit the box. Which leads us to the ultimate foundational corollary established in the text. P does not equal NP. And listen, it's not because we haven't found the right clever algorithm yet. It is purely because this computation is an irreducible topological invariant. According to the Titan knot theorem, the NP computation knot simply cannot be unknotted or simplified down to a polynomial rope length. It is already resting in its absolute tightest possible geometric form. But you know what? The source material doesn't even stop there. It zooms out to reveal a unified theory that is honestly mind-blowing. If P versus NP is just a geometric knot constrained by rope length, what happens when we look at the shadows of other legendary, unsolvable mathematical mysteries? Do they follow these exact same physical laws? This brings us to a concept the text calls the unified shadow. The source connects three absolute legends of math, Gödel's incompleteness theorem, the halting problem, and P not equal to NP, and argues that beneath the math, they are all the exact same topological shape. They're all, at their very core, irreducibility theorems. It's like finding out three totally different mysteries are actually caused by the exact same thing. We can actually see this Betti lattice structure seamlessly applied across all three of these mysteries, and they kind of graduate in severity. First up, P not equal to NP is a knot with a super polynomial rope length, meaning it's finite, sure, but it's just way too big for our budget. Second, the halting problem is a knot with an undefined rope length. You literally cannot tie it with any finite piece of rope, no matter how long. And third, Gödel's incompleteness theorem represents a knot with an infinite rope length, meaning the lattice of formal systems has absolutely no maximum ceiling. So what really ties them all together is this profound geometric principle: the irreversibility of information underfolding. Normally, operations like compression or verification decrease the Betti charge of a problem, but proving these theorems shows that certain knots, whether they involve the self-reference of Gödel, the diagonalization of the halting problem, or the exponential branching of NP, contain a completely irreducible topological charge. No amount of computational folding or trickery can ever eliminate that core knot. I want to share this beautifully poetic takeaway taken directly from the source material. It says, "The knot is tied with a single piece of rope. The rope is made of Betti charge. Pull the knot as tight as you want. Some knots cannot be untied." Wow. It just completely strips away all the complicated computer science and leaves us with this stark, undeniable physical reality. By viewing computation through the lens of topology and rope length, we gain this remarkably clear understanding of why some problems remain forever out of reach. It really makes you wonder, doesn't it? If the fundamental limits of computation are actually geometric shapes, what other invisible knots are shaping the rules of our universe? Thank you so much for exploring this fascinating topological view of mathematics with me today.